Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
I know some people are coming over from CSE, so I thought I would wait one more minute. This is, the old PPRC. You can start whenever you want. Okay. Okay, maybe we should start. So it's a pleasure to welcome Serdar Kasiran from Koç University, Turkey, here this morning. Serdar is actually visiting for the whole week. In case people are interested in meeting him after your talk, let me know and I'll try to set up a meeting. Serdar is very interested in checking concurrent software by verification methods and testing methods, and he's going to describe some of that work today. He before becoming a professor at Koç University, he was at DexCirc, and before that he was a student at Berkeley. At DexCirc, he was working on hardware verification, and hardware is concurrent, of course, and I guess that's where the interest in verification and testing of concurrent software started. So,
thank you. Thank you for the introduction. So I'm going to be talking to you about the research we're doing on runtime verification of concurrent programs. To give you a little bit of context about where we're coming from, first of all, we're interested in verifying programs as they are without doing any abstraction. And we're interested in verifying concurrency errors. And we're interested in catching bugs, not exhaustive verification. This forced acronym is due to the fact that Vyrd is the name of three sisters in Norse mythology that weave together the threads of fate, multi-threading, get it? So V-Y-R-D, we had to change around the order of the words to make it look sensible. It's joint work with my student Tayfunet, who's an intern here this summer and sitting in the front row here, and Shaz. And it's also a collaboration with the Boxwood Project team from the Silicon Valley Center and two of my undergrad students. The talk's going to be, it's going to consist of highlights of one PLDI talk from a couple of weeks ago and two upcoming workshop talks. And it consists of three parts. Very roughly speaking, the first part, the runtime verification tool, Vyrd, is going to tell you about catching bugs that easily happen but go undetected during testing. The second part is going to talk about bugs that are a little bit more difficult to make happen. So we use a model checker to drive our runtime verification tool. And the third part is going to consist of bugs that are even more difficult to make happen. And to tell you a little bit more about these, Vyrd is a runtime refinement verification tool. It has low overhead and it handled industrial scale programs such as the Boxwood Project and file systems, and it did catch bugs that were previously undetected in these systems. What Vyrd does is it checks at runtime these two novel correctness criteria, which also were inspired by our experience with these industrial programs. And like I said, it gives you improved observability and more extensive checking than testing. The second part, Vyrd MC, improves upon Vyrd. It improves coverage, and it reduces instrumentation effort required for Vyrd by using an execution-based model checker. And that way you get more extensive validation from small programs. And in the third part, we, through devising a new coverage metric called location pairs, we try to answer this question. If I'm after concurrency errors, what other tests should I try to write? What other things should I try to make happen? And this metric also was inspired by high-level data races, atomicity and refinement violations that we encountered in real examples. So without further introduction, I'm going to dive right into an example on which I'll illustrate all of these ideas. Then I'm going to contrast testing our two notions of refinement. Then I'm going to tell you about the tool we checked refinement with and our experience with industrial designs using Vyrd. Then I'll tell you about how we add model checking and the coverage metric on top of all of that. The example we're going to use is a multiset or a bag. It contains integers and it can contain more than one copy of an integer, like 3 here. The representation for this is an array with 2 fields. The content field simply contains the integer. The valid field is a 1-bit true or false. And if it's checked, it means the number is in the multiset. If it's not in the multiset. The reason we have this example in the talk is because it's simple. It mimics patterns we encountered in real systems. And it's interesting because if you try to verify this example using atomicity by reduction or linearizability as your correctness criterion, they would declare it incorrect, but it's not buggy. It works fine. And it's interesting because this was the case with the Boxwood project and a file system that we looked at. If you use linearizability or reducibility as your correctness criterion, those systems would be declared incorrect, but they work fine. I'll start by telling you about the lookup method of multiset. It goes through the array one by one, acquires the lock for each array element, checks if the content is X. If it is, it returns true. If not, it keeps looking. If at the end it can't find it, returns false. Okay. Sure. Oh, this one? No, you haven't assigned anything. This is showing actually a corrupt state where, right, I guess it's a mistake. This doesn't really reflect that set. Just ignore this one. Sorry. Thanks. Next routine I'm going to show you is FindSlot. This is a helper routine for a method I'm going to show you on the next slide. And what it does is you give it a number. It finds room for the number in the array. Okay? And the way it does that is by, again, traversing the array one by one, by locking it. If the slot is empty, it puts X there and returns its index. Otherwise, it keeps going. If at the very end it can't find room for X, it returns 0. Notice that it doesn't set the valid field. So even if FindSlot found room for X, at the end of this, X is not still a member of the multiset yet. Now comes the interesting part, the insert pair method. What insert pair does, it tries to atomically insert a pair of integers, X and Y, into the multiset. And it does this by first finding a slot for X. If it can't, it says I failed. Then it tries to find a slot for Y. If it can't, it frees the first slot and returns failure. If both of these succeed, then atomically it sets the valid bits of the ith and jth slots to true. And at this point, X and Y have become members of the multiset. And although it looks contrived, this example is representative of projects we looked at. Because many methods try to get hold of a number of resources. And they don't do that in one locked big atomic block. They do that in separate atomic blocks. But once they succeed in doing all of that, at the very end, they suddenly make their work, the result of the operation, visible to other threads. What's also interesting about insert pair is it has this interesting exceptional termination scenario that's not possible in an atomic linear execution. So imagine that I have a very small multiset, an array of size 2, and I'm running 2 concurrent insert pairs. Okay, and the interleaving happens so that both of them succeed in their first part, so they both find slots for their x's. Okay, and then the array fills up. They both fail to find slots for their y's, so both insert pairs fail. Well, if I had an atomic execution, the first one that went would find slots for both of its x and y, and it would have to succeed. So this scenario, although it's not buggy, although it's fine in a concurrent program, is not possible in an atomic execution. So criteria like atomicity or linearizability that say for each execution of your system, there should be an equivalent linear execution, declare this one incorrect, although it's not buggy. This point's sort of crucial, so maybe I should pause here. Yeah. When I define what our correctness criterion is, IO refinement and view refinement, according to those criteria, this is a fine example. Yes? That was on the previous slide. It goes through the array one by one, checks if there's an empty slot. If there is, it writes X there and returns its index. Okay, so it says I found room for X. Here's the index of the slot. Okay.
Second FindSlot to update the contents of A sub I is not locked.
Right. So that's also what makes this example interesting. Here there's a race condition, but it's benign. Here I'm simply freeing the ith slot. So if some other thread comes in before I free it or after I free it, the data structure doesn't break. It just says, well, the other guy found room or didn't find room for what he was looking for. Do I make sense? Okay.
Buggy program, because another insert there could have thought that it was going to use A sub I, and now it's getting wiped out on it, and it thinks that it's
So what I do when I reserve a slot for myself is I put the number there. Okay, so it's no longer null, and the next guy that comes, if he wants to write, he checks, is it null? It's not, so he skips. Right. And again, this looks contrived, but it was exactly the case with some of these very highly concurrent tree algorithms in Boxwood.
So I'm sorry, there's two things that are about each of the array. The fact whether it is null or non-null.
Mm-hmm. Yes. What is it?
Can something be valid? Something be not valid until the content be
mm-hmm. So that means I've reserved the slot for X, but I don't know yet. Let's look at insert pair. So the reason I have this is I want to first make sure that I have room for both X and Y. Because if I insert one and not the other, that's going to be an atomicity violation. Okay, so first I write X in there. I reserve the slot, but I don't set the valid bit yet, because I don't know if I'm going to find room for Y. Okay, I keep looking. If I find room for Y, then inside this locked block, I set both valid bits to true. Yes? Yes. Yeah. But that's not all we need for correctness. We need more. Mm-hmm. Right, but content not null does not imply valid. Okay. All right. Later we'll see that we also can handle separately given specifications for data structures. And the way we want specifications to be written is in the following fashion. The interpretation is that the specifications methods perform an atomic deterministic state update. Okay, so let's look at insert pair. You give it the two numbers plus what's the return value of insert pair. It says if I succeeded, then I update the state to include X and Y. If I didn't, I do nothing. Okay, the other ones are straightforward. Yes. It's a multi-set. So this should really say multi-set of integers. All right. So we paid the price. We learned about the example. Let's, on this example, contrast these three. So let's suppose I was trying to run a multi-threaded test on this multi-set example. And suppose the following execution happened. Time flows from top to bottom. Each box indicates an atomic action by one thread. Each color is a separate thread. Okay. And notice that the insert method and its return point and the delete tree and its return point are such that the lifetimes of these two operations overlap. Okay. So if I had run this test and if at the end I wanted to know if 3 should be in the multiset or not, since I don't know which one of these happened first, I should allow both 3 in the multiset and 3 not in the multiset as correct outcomes. So just one second. So I'm forced to be too permissive, too loose. And what we found in the examples we looked at was the common practice was to run a long multi-threaded test, but on the final state, just do some sanity checks and check things like if the valid bit is set, it's not null, but not necessarily the contents of the multi. Vyrd?
Please present multiple times and delete one instance of it or all of it.
Just one. Right, but suppose I started from an empty multiset, and I know that these two happen, but I don't know which one happened first. Okay. Again, it's a little example of concurrent operations whose order you don't know, so at the end you don't really know what your data structure state should look like. Just return. So that part is contrived. So let's see what I/O refinement does on top of this. This is our first novel notion of correctness. Again, we have the same execution here. I/O refinement says, corresponding to this execution of the implementation, there should be a spec trace. Remember, the specifications methods are run atomically, one at a time, starting from an initial state. Okay, and it says there should be a spec trace like this, on which the call and return actions in each thread match. So if I look at the red thread, the call and return should match this call and return. If I look at the green thread, they should match, etc. Well, what we don't know about this spec trace is in which order these operations happen. Okay? And the trick we play there is, we call it commit points. We ask the programmer to annotate his code or to select some actions in the lifetime of each operation as the commit action. For instance, if I'm doing insert 3, if I unlock the 0th array element, that's the point at which the operation commits. Just 1 second. And the ordering of the commit points for each operation give me this order. Okay, so I get rid of trying all possible permutations, etc. I end up with one order, but I'm really cheating because I'm asking the programmer to give me that order. Yes? What do you mean? Well, we believe you can. Could you give one example like that?
Commit point depends on what happens.
Right, so how should I put this? So think of this as us asking for a hint from the programmer. Okay, so I/O refinement just says there should be such a trace. The way we check it says, let's ask the user for a commit point, and let's check that trace to be computationally efficient. Okay. But that example maybe we could discuss after the talk together, or in a few slides. Yes? Let me go on for a few slides and then ask that question. Okay. So I/O refinement says for each trace, execution trace, there should be a corresponding spec trace where the call and return actions per thread match. The ordering of the operations here I get from commit points. Maybe I should just jump into the commit points. So like I said, we use them to determine the witness ordering, to drive the specs execution. And they're not formal concepts. They're hints to the refinement checking tool saying, please check this spec trace to see if it does what I want. And as such, there's no formal procedure for selecting them. But intuitively, we believe that the programmer has a pretty good idea where his commit point is. We mean the commit point to be where the new updated data structure state becomes visible to other threads. So if we look at this example, for instance, the place where you unlock the first lock after setting these valid bits is the commit point. Because at this point, some other LookUp thread, for instance, could come along and see that AI is valid and it has X in it. Okay, before here is not the commit point, because although X and Y do reside in the array, the valid bits are not true. And it's not the commit point here because another thread can't come along and access those because they're locked. Okay. So the programmer thinks it's after unlocking these that I make the new multiset with X and Y included, visible to other threads. So he marks this as the commit point. Yes? Mm-hmm.
So the idea when you mentioned that IO refinement is a weaker notion and serializability. So that definition, one can look at that definition even without actually considering commit point.
Mm-hmm.
Computation.
Yes, yes, yes. The fundamental difference is we have a more permissive specification. Meaning, if you look at the insert pair specification here, it allows failure. Okay, and remember the two slot multiset example where the first one has to succeed. Okay, this specification allows it to fail even when there is room to model the case where there is contention for resources, and although there are resources for one of them to succeed, they still fail.
Perhaps another way to put it is that serializability doesn't come with an abstract set.
Mm-hmm.
In terms of concrete implementation. If all the properties are same in terms of concrete implementation.
Right. Linearizability, that's not generally true.
Yes. With linearizability, there's some confusion in my mind about exactly what it says.
Right. So let me get to that. So this is I can't seem to find it. Oh, here. Okay, so this is as exact a quote as I could remember from the linearizability paper. It says each execution must be equivalent to an atomic linear one that satisfies the sequential specification for the object. Okay, it's not said in detail what this sequential specification is. So you can think of IO refinement as not something entirely different, but something where with this sequential specification, we mean a more permissive specification where you allow different sorts of termination that models concurrent execution. Yes?
More permissive specification, which actually satisfies serializability.
I thought IO refinement was more catchy, but I can go with that too.
One implementation of the specification. The innovation doesn't seem to be in the notion of refinement, but in the notion of what the specification is.
Yes.
Just from understanding.
Yes. And the novelty will actually come when I talk about view refinement. That is very distinct from linearizability, and we'll see that the more interesting refinement checking is with view refinement. Yes?
That's the notion that people have used, is the notion of linearizability. It is given respect to effect. For example, there are linearizable data structure implementations that don't get something that could result from a linear execution.
Mm-hmm. So there exists a separate specification that says... Right, okay. So, I mean, I'm not that intent on this point. If linearizability with the non-deterministic spec, if linearizability plus a spec written in this fashion is what linearizability means, then IO refinement is linearizability. Okay. So we already saw a little bit how refinement gives you more observability than pure testing, because you know what the end state is supposed to be if you know the order of the operation. Now, let me motivate the next notion of refinement that we call view refinement. Okay. Now, imagine a buggy FindSlot implementation where before checking if a slot is available, I don't lock that element. I lock it only afterwards. So, as it happens in this case, two threads can come along and they both read the 0th slot and think, this one's available to both of us. Okay? And then thread 1 goes along and happily does its job, writes 5 and 7, sets the 5 and 7 valid bits to true, and then it says, did I do it right? Are 5 and 7 in the multiset? It checks them, and everything looks okay. Okay, then comes along thread 2, it thinks the 0th slot is available to it, but it overwrites the 5 that the other guy wrote. Okay, and it goes on and writes the 8, and at the end it says, well, I inserted 6 and 8. Did I do my job right? Check 6 and 8. Looks like everything's okay. But everything's not okay. The end state is wrong. Okay. If this lookup 5 had gotten interleaved here, it would have caught the error, but it didn't. Okay. And if you imagine the extreme case where you do no lookups, you won't catch any error through testing or IO refinement. Okay. Or it could be that eventually you do a lookup 5, but 1 million method calls from now. Okay. And you realize 5 isn't in the multiset, but the origin of the error is too difficult to trace. Okay, so the idea here is, well, if we looked at states more carefully, if we had a correctness criterion that actually looks at state, looks for a correspondence between implementation state and the spec state, that would be better. And that's exactly what view refinement is. It catches a state discrepancy at the next commit point, and in that way, it's an early warning for possible future IO refinement violations. Okay, and the way we do that is by what we call view variables. One variable for the implementation, one variable for the specification. And these hypothetical variables, I mean, we don't add these to the program. The checking tool does this. They capture the abstract data structure state, and they get updated atomically once by each method. For instance, for the implementation, what we do is just pick the element whose valid bits are set and get that multiset. That's the view for the implementation. For the spec, because it was already abstract enough, the view and the spec state are the same thing. But this shouldn't mislead you, because later I'm going to show you an example of a spec that's actually a program, and that has state to be abstracted away. One other use of the view is to canonicize data structure state. For instance, these two representations are the same multiset, but they appear in a different order. Or you could imagine hash tables of different sizes or different hash functions, but they have the same contents. And the view variable is the result of an abstraction function, and that abstracts those away and canonicizes it. In this case, you just traverse the array, pick the elements whose valid bits are set. Okay. Then, what we do is exactly like IO refinement, except we don't only check the call and return values. We now require that the commit actions be labeled by the value of view. Okay. When the commit action happens, we traverse the spec state or the implementation state using the abstraction function given by the programmer. That gives us an abstract state or the value of the view variable. And we require that this match with that, and this match with that, etc. So if we go back to this buggy example, what happens when the second insert pair commits is that the view of the implementation has only 3 elements. The spec one is supposed to have 4, so here's a discrepancy. At the last commit point, views matched. So we say, oh, the error must have happened between here and there. Let's look carefully at this trace, at that trace, and see what went wrong. Yes?
The view, don't you need to lock potentially the entire data structure to compute the view?
Yes.
The point of view, how do you lock?
Right, so we don't do it really by freezing the program at runtime. We log stuff, and then later we reconstruct the frozen state. I'll show you the architecture of the tool in a second. Let's see.
Other traces, since you don't have these view refinement, the bug will be detected by some other trace. But the point is that you want to find this trace itself.
Yes, exactly. So if you look at this one, right, in this trace, the bug did not appear, but it doesn't mean it will never appear. If I had done different lookups, if lookups had gotten interleaved differently, the bug would have propagated to a return value eventually. But here, I catch it right when it happens. Okay? So I guess this is really the crux of the tool. When I said it catches errors that happen but aren't detected by testing. This is what I'm talking about. And this was the nature of the bugs we found in Boxwood and the scan file system, etc. The bugs were happening very easily, but making them show up at the return value of a method was the difficult part. Since I talked about that, maybe just I should skip ahead to the... no, I won't. OK, so the tool looks like this. We instrument the implementation. And as a multi-threaded test is being run, it writes actions into a log in the order that they happen. And this log, there are tricks to make this log interfere minimally with this. The initial portion is in memory, etc. And also the commit annotations are in the program, so the commit points are marked in this log. And the other thing we ask from the user is if he wants to do view refinement checking, he needs to write an abstraction function. But this is all the interference we have with the tool that runs. The rest can happen online on a separate thread or offline after the fact. We read actions one by one from the log. We have a replay mechanism that on one side runs an instance of the spec in the witness ordering, according to the order of commit points. And on the other side, it runs a separate copy of the implementation for exactly the purposes you pointed out. I want to freeze it in time, traverse its state, compute the abstraction function, and I don't want the user to worry about locking, etc. when he's writing the abstraction function. So I get a trace here, I get a trace there, and I either check IO refinement or view refinement based on the order of commit points. Yes?
Abstraction function might touch in order to be able to do this, right?
Yes, yes. And I don't have a slide about that because it's too much detail, but you can do that at different levels of granularity. For Boxwood, there was already a coarse level of granularity at which you could do that. But for verifying the Java libraries, for instance, we had to log every write to every variable.
Every write to every variable, not the variable.
Right, every write to every variable. Yes?
And maybe multiple commit points for every transition.
Yes, and that's again a tricky point that I was trying to avoid putting on a slide. It's a long story. I can tell you about it after the talk. Basically, if you really want to know where the commit point of a read is, you have to wait till the end of the method. You have to log every read. You don't know which read is going to tell you the result of the operation, and that's too expensive, so we do something a little cheaper. Yes?
So in order to log the spec and to read the whole thing.
Log the implementation, you mean?
To compute the multi-set.
Uh-huh. Uh-huh.
So you have to log the whole thing.
Uh-huh.
Even on the read.
Yes, but I do that on this separate copy that I'm running only for verification purposes. The actual implementation is going along happily. So if I'm running this on a virtual machine, I run the same bytecode instructions here. Or if I've logged at a higher level, which was the case with Boxwood, there was already a replay mechanism implemented for recovery purposes. I mean, Boxwood is trying to be fault tolerant, so it logs and has a replay mechanism to recover. So we just use that. But that's an important point in the usability of this tool. And I'm going to talk more about that. OK. So that's the tool. But what if you don't want to write a separate specification? Is what you're doing going to amount to testing? Well, we have this trick called atomizing an implementation. Well, it's being used by others too, I guess. And the idea here is you're thinking your implementation, if run sequentially, you're fairly confident that it's correct. Or you can say you're going to worry about verifying it sequentially separately. And you're interested in concurrency errors now. So you say, I'm going to assume that if my implementation is run atomically, it's correct, and I'm going to make it look atomic by declaring one global lock. And any method, before it runs, has to acquire this global lock. And when it's done, it releases this global lock. There's one difference. We still keep the permissiveness. Is that a word? So we change it a little bit. We change it to read in the fashion of, here's the return value, take me to the end state. For instance, your insert pair, here are x and y, here's the return value. If the return value was failure, just return failure, don't do any modifications to data structure state. Other than that, it's the same implementation. And now you can run this atomized copy as your specification, and you don't have to write a separate specification. Okay. These notions of correctness and the tool architecture, etc., in fact, most of our work was driven by the Boxwood project. And for those of you who don't know, this is a storage infrastructure project that makes abstractions available to its users. It consists, the portion we looked at consisted of 3 modules. The chunk manager module, this is the distributed storage infrastructure. There's a B-link tree, and for performance purposes, this sits on top of a cache, and the cache talks with the chunk manager module. And all of these modules are very highly concurrently accessed, and especially the B-link tree module uses very loose locking to improve performance. It consists of, the portion we looked at consists of some 30,000 lines of code. We, in fact, experimented extensively using Vyrd on other examples. An earlier prototype we had worked on was the scan file system. We looked at Java libraries, earlier versions with known bugs, and some other data structures that we cooked up, tricky versions of multiset, etc. And on all of those, with moderate annotation effort, several lines to mark the commit actions in each method, and with low overhead, it was able to run and, in fact, catch errors that had previously gone undetected. And to give you an idea of what overhead is like, for the B-link tree, these are the better numbers. There are some worse numbers, but none of them have overhead of more than 400%. For the B-link tree, logging added 17% on top of regular testing time, and the refinement check added 27%. If we did view refinement, we had to log more stuff and do a more thorough check, and that added 20% over testing and this many percent over refinement. Refinement added this many percent over testing. And to illustrate how view refinement is more effective in catching errors, the bug that I'm going to describe to you on the next slide. With view refinement, after 26 random method calls, it was triggered and showed up in view refinement. In IO refinement, it showed up after this many random method calls, and it hadn't been detected by the developers earlier. And in the current version of Boxwood, this bug is no longer there. And wants me to say this. Now, I want to tell you about this interesting bug because it both illustrates what view refinement gets you, and it was the same kind of bug that appeared in the scan file system and in the Boxwood cache. And the way the bug manifests itself is you have a cache, and below it you have permanent storage. The cache contains correct data, but the permanent storage has corrupted data. Okay. And let me tell you the cause of the bug later. And it's very hard to cache through testing to make it propagate to the return value of a method, because as long as your reads hit in the cache, they return the correct result. You don't ever access permanent storage. So to make the error visible, you need to play with the cache, fill it up until it evicts that entry, with no writes to the same entry in the meantime. And then you have to read that entry, retrieve it from permanent storage, and get the corrupted result. So in both of these systems, this error was there. In the scan file system, it had been there for several years, and it had never propagated to the return value of a method. But when we ran refinement checking, it was pretty much within the first test that we ran, the bug showed up. Yes. No, because you're thinking it's clean. You think you wrote the correct data to permanent storage, but it's dirty. Dirty. Yes.
That's the function you have if you just taken it and run it as an assertion set in the original program.
It would have caught this. It would have caught this if well, our abstraction functions have some assertions inside them. When computing state whose bits are here and there, for instance, if I wrote an abstraction function for multiset and it said just take the entries whose valid bits are set, but one entry had the valid bit set, but the element was null, then I would have a multiset with a null element in it. To prevent things like that, we have some built-in assertions inside the abstraction function. So the abstraction function can compute a proper value only if the state is consistent according to some well, if you hadn't thought of it before, your abstraction function would have some garbage inside it, and it wouldn't match the specs. So, pardon me? Yeah. Okay. All right. So, up to here was how runtime refinement checking with view refinement improves upon testing by giving you more in-depth observability into your program and gives you early warnings. But now let's look at a case where you still have this bug, but it so happened that T1 and T2 don't both look at A0 one after the other. Okay, so although the bug is there, because you didn't exercise the interleaving, the bug isn't even triggered. In that case, view refinement, IO refinement, or testing are the same. They don't give you anything extra because the bug is not triggered. So the next step was, well, how can we more systematically, more thoroughly exercise thread interleaving to make bugs, to trigger bugs that don't appear during random testing easily? Okay, so it was our experience with some of our contrived designs that if you had very long tests with many threads, the bugs were exercised. So we thought, well, how can we try to exercise those without doing this? Or how can we exercise bugs that don't even happen when we do this? And the idea is fairly simple. We're doing a very constrained, a very limited application of model checking, where we're running a small number of concurrent threads, each running one operation. And using an execution-based model checker, we're exploring all distinct thread interleavings for these three. So the idea here is to not explore really the data or the other program state component of model checking, just to concentrate on the concurrency component of the state space. And of course, to make this fixed test more interesting, we want to start with a non-trivial, interesting enough state, not from an empty tree or an empty multiset. So we run a long sequence of random method calls to create what we call an anchor state, an initial state, to start this small multi-threaded test from. And then at the anchor state, we start the model checker, and we make it examine the different interleavings of the threads. And this part is really more a guideline than a technique. We try to pick method arguments so that the different threads are trying to clobber each other or to work on the same part of the data structure.
Different threads are always using different methods. Is that right?
Mm-hmm.
And what is the worst condition if you decide two threads using the same method? You wouldn't find it there.
Oh, I mean, different methods meaning they could both be doing, for instance, an insert 3 or insert pair 5, 7. They could both be doing that. Yeah. Sorry. Now I get what you were asking.
The model checking phase.
Mm-hmm.
And that program, that's handcrafted or that's randomly generated?
Program
that's executed in the model checking phase.
Right now it's handcrafted. Now we're getting into the workshop paper part where we're a little less cooked. My answers are going to be a little bit more hazy. So the idea is, now that you have this fixed program, if you're method implementations don't have infinite loops in them and stuff. Your state transition graph is a DAG, and when the model checker explores it, you get this exploration tree. And this tree consists of just the same method calls being executed, except the thread interleaving is different. And it doesn't mean they consist of reordering of the same actions, but it's just the same method calls running in different interleavings. And the model checker walks you around in this tree. And instead of running, say, an assertion or a temporal logic formula as your property, you're running refinement along with it. And this brings with it
when refinement was happening, refinement checking was happening after the fact.
Right? How is that physically? So right now it's not happening in a separate thread because there's no reason. Before we run it in a separate thread not to interfere with the program's regular concurrency behavior. Now the concurrency is controlled by the model checker, so we don't care. But the refinement tool was implemented thinking the log we have is linear. It starts from the initial state, and my state is determined uniquely by replaying the actions from the beginning to where I was. Now we're exploring a tree. There are backtracks, jumps in it, etc. So now the log needs to be a little different. It needs to mark these jumps back in the log. And also, the refinement checker has a lot of complicated extra state, a lot of history information that it retains with it. So instead of trying to undo things or rewind operations, what we do is when there's a backtrack, we simply restart from the beginning. Not the very beginning, but from the anchor state. And then we go down this other path, and the entries are marked properly so that when we're replaying these guys, we skip over these ones. Details are in a paper.
That are currently abstraction functions, so we can just examine them, right?
Wait.
So the abstraction function, right?
Well, there are two answers to that. It depends on what model checker you're using. Okay, so I'll tell you the... okay, if you're using a stateless model checker, such as Verisoft, okay, then you don't have access to state directly, so you have to still do the logging. Okay, but the version that we're right now implementing on Java Pathfinder is like how you said, it has the nice extra benefit that the logging and replaying of actions, the question you were asking earlier, now it's streamlined because what you log is a bytecode instruction. What you replay is the same bytecode instruction in the same virtual machine that the model checker runs in. And you don't have to worry about the semantics of replay because it's a virtual machine. So it helps with that more difficult part of instrumentation if your program didn't already have that. So now the programmer only needs to write the commit point annotations, and like you were saying, Shaz, you can just run the abstraction function on the state of the data structure. Yes?
Source of bugs you've already found. You can go further back in the trace and think of this as a local search from arbitrary points earlier in the trace.
And oh, I see. Yes, or give me a trace maybe with fewer. I mean, it could be that the random trace that triggered the bug had a lot of other thread switches that had nothing to do with the bug, and this could give me a simpler explanation. I haven't thought of that.
Yep.
Okay. Should I try to wrap up in 10 minutes or so? Why don't I fast forward through some of this and tell you about the location pairs metric. So, so far we did view refinement, got more observability. We ran a model checker on fixed test programs and explored different interleavings. But there will still be some interesting concurrency errors that neither of these will get. And if I'm the programmer and if I want to answer the question, what other unexamined scenario should I try to trigger? Clearly, I can't look at the entire space of executions, like I said in the beginning, we're interested in industrial scale programs and we're interested in verifying them as is, so I don't hope to complete model checking for interesting big states. So then what other test input should I give to refinement checking? That's the question we're trying to answer in this part of the talk. And the way we do that, the way we try to formalize that is through a coverage metric. And this metric serves as a link between testing. Yes?
That random sequence of method calls that was made to get to the anchor state, and then the program that each thread was executing the method calls. That's what you mean as test input, right?
Right. Well, the picture isn't as integrated as I made it sound, I suppose. So what I'm telling you now is you're going to run refinement checking, and you're thinking, what else can I test? You're not necessarily going to use model checking, but you're thinking, what may I have missed? So the idea here was, the idea we had in the back of our head when we were trying to formulate this metric was, let's focus on concurrency errors only, not at the data or the rest of the program state. And let's have this kind of concurrency error. High-level data races, atomicity violations, refinement violations. So everything could be lock protected properly, but not the atomic SSH. And so actually, let me show you two pictures and then the idea of the metric. So this is the bug in an earlier version of string buffer append in Java that some of you might be familiar with. So the idea here is you're trying to append the string buffer SB to this string buffer. So first you get the length of SB, and then all of SB's methods are synchronized. So you get this atomically, and then you try to get the characters from SB atomically, but in between, SB is not locked. So somebody else could come along and change the contents of SB. In this example, there is the setLength method. Somebody could just set the length of SB to 0. Maybe you think you have 100 characters, and then you try to read them. They're no longer there. Okay. So here's the interleaving again in time that shows you this bug. And the feature that I want to draw your attention to is this error occurs whenever this interleaving of events happens, and there's a data dependency between this and that, meaning the setLength method is called on the object who I'm getting characters from. Okay. Notice that it's not dependent on what length I'm setting it to, what SB is, what the contents of SB are, etc. It just says if this happens after that, and if there is a data dependency between here and here, this bug always occurs. Here's the bug from Boxwood cache in code form. So what this method is doing is it's flushing the data that's in the cache to permanent storage. So boxmain.alloc.write is writing the data in TE to permanent storage. And copy to cache takes this byte array buff and it's copying it into the cache. And the bug happens when you've written part of the data to the cache, but you haven't finished writing the buffer. You have a byte array, you've written half of it, you're not done writing it, and then flush happens because of not proper locking. You write half old, half new data onto disk or to permanent storage, and then you keep on copying the rest of the data onto your cache. Okay. So this error again is triggered whenever this code block is followed with this code block, and they touch the same bit of data. Okay, one reads from it, the other writes to it. Okay. So, in fact, if you look at bug descriptions in papers or in some bug reports, the bug report goes like this. It says, method 1 executes up to line X, and a context switch occurs. Method 2 starts execution from line Y. And provided there's a data dependency between the code executed up to here, block X, and the code executed after here, block Y, the error is triggered. Now, to make this interleaving happen, you may have to do a lot more about the program state. I mean, you may have to have, I don't know, in one example, you may have to have 100 threads concurrently going on to fill a hash table. Okay? But if you look at the code, you say, well, if I want this code block to follow this code block, then the hash table must be full. So this gives you a handle about what complicated thing you may have to try to make happen to trigger the bug. Okay. So the idea here is to, let me fast forward. So it's strictly as an aid to the programmer to give him more interesting scenarios that he has not considered to try to test. Okay. So when I formulate the coverage metric, there will be problems with it. When I say, well, here's a coverage target, it will be undecidable whether that's reachable or not. Okay. And also, it will be the topic of another research project to come up with a good approximation of what targets are reachable, what targets are not reachable. But if through doing all of these things I told you about, if you can't rule out one coverage target, then as the programmer, it would be a good idea for you to make sure that nothing goes wrong if that interleaving happens. Okay, you should either argue to me, help my tool rule out that coverage target, make formal your reasoning why you think that can't happen, or you should assume that it can happen, and you should make sure that everything works all right in that case. So the metric just, okay, the beginning point of the metric is to get the control flow graph of each method, and then to mark locations. And between each location, each pair of locations, there's an atomic action or atomically executed chunk of code. Okay, and the name of the metric derives its name from these locations, and the pair comes from looking at a pair of methods. Okay, so if you look at the coverage criterion, we describe it in the form of a finite state machine. Okay, and the finite state machine state consists of 3 components. The first component says I'm looking at one method's body, what location am I in, and 1 bit of information that I'll tell you about in a bit. The second part says what location am I in the second method, and the last bit says do the actions following the first location in method 1 and the second location in method 2, do they have a data dependency? And the way coverage state evolves through time is, suppose you're in location L1 in one method, L3 in another method, and you take the transition from L1 to L2 in thread 1. Sorry, this is it doesn't have a, okay, you took the transition from L1 to L2, okay, and before you took that transition, it was the case that code that followed these 2 locations were dependent. Okay, now you're thinking, okay, the 2 code blocks were dependent, and I just took an action in thread 1, so now I want thread 2 to follow with his dependent action. So you set pend2 to true, okay, and when thread 2 does follow with that code block, then you reset pend2 to false. And we require that these blue transitions, where you say, well, I want to follow with the proper code block that has a dependency on this one. On this coverage FSM, it's your target to cover all these blue transitions. And you are to do this for each method pair. Well, what if one method calls another method inside it? We're going strictly by code coverage, and we treat that as one line of code. Well, what if there's interesting concurrency inside method 3? Well, that gets considered when method 3 and method 2 are the pair that form the FSM. So you could think that it's quadratic in the number of methods, the number of things that you have to look at. And
you want, for example, there's like hugely different behavior when method 3 is called from method 1, or if it's called from method X.
No. I mean all of the data dependencies in this 1 bit. Okay, all we care is this location followed by that location, and there's a data dependency. That's all we're looking at. And we have a number of ways in which you can reduce the number of locations that you have to look at. For instance, if you have a sequence of method local actions lines of code, you can consider all of those as one atomic action. And there's a way you use purity, which is really useful, but maybe I won't get into it now. But I guess I should tell you about this one. So the way we justified this metric was by looking at the bugs that we caught and by looking at bugs that other people caught and recorded, that they reported in papers or online. And in all of those cases, it was the case that if you had accomplished 100% coverage according to our metric, you would have caught or triggered the bug. Sorry, not caught. The catching part comes with refinement or some careful looking, but you would have triggered the bug. And to give you an idea of, well, what if I have millions of locations? In Boxwood's methods, which are fairly large, if you do these collapsing of method local actions and purity, etc., you end up with roughly 10, is that correct, Typhon? Roughly 10 locations per method in Boxwood. And if you ask me, well, if I did a bunch of random testing, how many am I left with? Or how does coverage ramp up over time? I don't know. My students are about to send me their final version of their coverage measurement tool. So to recap, I told you about 3 related pieces of work. A runtime refinement checking tool, how we add model checking to that to improve coverage, and a related coverage metric and a measurement tool to help you write tests to use the first 2 tools. Thank you. Yes.
It suffices to have appearance of 2 threads from some state.
Mm-hmm.
Of course, we can construct example with the initial threads.
And I would argue that I'm sure you could construct an artificial example. But in the ones we looked at, the function of that 3rd thread was to set up the beginning state for the interaction of the other 2. Yes?
If you're doing especially linearizability, there are real examples that take 3.
Well, I know, for instance, this some Microsoft code, I can't remember what, with this I don't mean there are only 2 threads in existence. I mean, you need 100 threads to fill up a hash table, and then the 101st to... Yes. I'm sure you could, but this was one interesting beginning metric to look at. Yes?
Very widely read, but there's a tool that Keir Fraser described in his thesis for linearizability. And that's quite interesting. It doesn't use any program annotations of linearization or commit points, and has some heuristics that, although not guaranteed to be able to find a linearizable schedule that exists, seem to be very good in practice.
Mm-hmm. I would like...
wouldn't work well with these pen that non-conflicting operations on its structure based on parameters passed to them.
I see.
One where his scheme doesn't work well, but it must do it.
I would like to take a look at that example, and probably so would my student. He's right now working on a technique that helps automatically come up with the commit point, among other things. So, in fact, if you follow a certain programming pattern, we can tell you where the commit point is, but like you said, it won't work in some cases.
It's like the case mentioned where the commit point is the last time the thread executed a certain instruction.
Mm-hmm.
The last time that executed this instruction unless the concurrent thread executed this other instruction.
Yes. If you try to, for instance, come up with a commit point for LookUp, and if LookUp was returning failure, the commit point would have to be the first time it reads a location. I mean, okay, suppose you're running LookUp, you look at the first array box, and X is not there, but after you, somebody comes along and writes X there. Okay? So for you to have determined the commit point for LookUp correctly, you have to say the first time I performed the read. So you know that the commit point is the first read only when you return false, and it was at the very beginning. So for what we call observer methods, we have some different checking. We basically look at between the call and return points and look at all the abstract states in between. And we say if the return value is consistent with any of those, we declare it correct. That does not modify. Right.
Is it true that this kind of complication occurs only with, well, maybe in practice with observer methods?
Probably not. I mean, again, with insert pair, if you're returning failure, let me think. No, because when you return failure, you're not modifying abstract state. It doesn't matter where the commit point is.
It returns state like an observer method, maybe.
Mm-hmm.
Success state is not an observer method.
Right. Right. So if I'm returning failure in insert pair, the first read that the first FindSlot did is my commit point. Well.
Where they can update, but the linearization point is kind of a similar way to these observer methods.
I see. So actually, I mean, that's another bit of complication I hid under the rug, but Typhoon's implementation has these annotations of possible commit, pre-commit. This is a commit action on the condition that the return value is such and such, and you just write that into the log, but because you're doing the checking after the fact, you can look at your entire execution and pick the one that's your correct commit point. But that said, although there are such tricky examples, in the ones we looked at, it was fairly straightforward to define the commit point.
Thank you.
Oh, I'm sorry, I couldn't. The LP metric? No, that has nothing to do with commit points. You get the control flow graph of the method code, and all of that is automatic. No.
Okay, let's thank you.